My name is Véle, and I will present you some information about topology optimization in additive manufacturing. First of all, why it's need to run the topology optimization. The additive manufacturing is still a very expensive process. You need to think about how many material do you need for the part you wanted to produce. So the best option how to design the parts is use the topology optimization or different type of design purposes or the approaches. So what is the design for additive manufacturing? Basically, you have to think about the product that should be less weight, use less material as possible. You have to use the advantages of the simulation for additive manufacturing. You have to know the limitations of the technology, the machines that you use for the production, and the materials. This point is very crucial because the material has a different behavior in different directions. So what is topology optimization? It's a mathematical approach for distribution the material in part. The input into the topology optimization is first the design space, the boundary conditions, loadings, mechanical properties of the material, and the outputs are displacements, stresses. The topology optimization can be controlled by displacement, stresses, stiffness of the final part, or the final weight of the part. And how it works. First of all, you have to define the problem of the topology optimization, so you have to find the design space. For imagination, let's say it's a cube that with specific points that will be the loads and the forces, support structures, and etc. And you have to define the functions for the topology optimization process. This function runs the simulations and leads to the final result. After optimization, you'll get very rough data, and you have to create a step file or the STL file, and then run the simulation and confirm the results from the topology optimization. The first approach is a solid isotopic material simulation. Basically, this approach marks the elements with 0 or 1, or if it's the value close to 0 or close to 1, it just move the element to 1 or 0, and after each cycle of the optimization, there will be left some elements, and then you have again the force loads and the support structure and the structures, and run the simulations and again. And after a few steps, you get the final shape of the part. The second one is bidirectional structure optimization. This optimization is much better for topology optimization because the main advantage of this approach is that you can add some elements if it's need to be add into the volume that you are running the simulations. So if there are some high stresses, the software or the approach can add some elements, and next step will be with much better results. So main advantages and disadvantages of topology optimization. So the main advantages are you can create lightweight parts. It's very crucial in additive manufacturing of metals. You can also reduce the number of parts in assembly. It's very important in some applications, for example in aviation and aerospace. And then you can create the design that is printable without support structures. Is also very important, because after the printing you have your model can be surrounded by support structures, and it takes a lot of time to remove the structures without indenting the part and make some cracks in it. And also the topological optimization are very important in time and cost reduction during the manufacturing. Disadvantages: it's a very time-consuming technique in early stage of setting the model, because you need very skilled professional that can set the model correctly and run the simulations in a way that should be. This technique is also dependent on knowledge of simulations, additive manufacturing process, material behavior, etc. After simulation you will get very weird geometries that requires a lot of work with surface modeling. So it's important to know how to do the surface modeling. So there are some softwares that can be used for topology optimization. The first one is Altair Inspire. The second is NX Topology Optimization, which was used in a case study that I will show you later. Then there is ANSYS Additive Suite and the platform, which is really good because it's free for students. And there is Creo, Fusion 360, and etc. The Altair Inspire is also very good because there are some really good functions with that can help with reshape the model after simulation. They call it polymorphs, and you will see the results from this software. So the case study that I will show you contains two software. For the optimization was used the NX Topology optimization, and for the reshaping the design was used the Altair Inspire. So there is the case study. So I choose the bike stand, and on the left side you can see the reference bike stand, which is the regular one which you can buy in the shop, and on the right side there is my result from the topology optimization. The parameters for the bike stand are the length is 100 millimeters, and the steep is 6 degrees. So first of all, the reference model was the mountain bike stand. The method was used the topological optimization in software NX Topology optimization. Material was chosen the aluminum alloy, which has almost the same mechanical properties as the aluminum 6061, which is regularly used for bike parts. The input parameters as loading and boundary conditions were taken from the standard ISO 42105, which is used for the testing bike components, and measured output parameters were maximum stress and displacement. So there are some information about the material. The yield strength is 220 megapascals, and which is basically the number that the simulation will take as the maximum value of strength in a part. So stress, sorry, not strength, but stress. So I used a free test from the standard for testing the bike stand. The first one was a side bending where was the force with 1000 Newton applied on on the board, side of the handlebars. I can say that the handlebars were 600 millimeters long. And the second experiment was the forward bending with two settings. The first one was 1600 newtons and the second one 2600 newtons. For passing the test, the results will be seen in the next slide. But for the second test, which is forward bending, the one bike stem has to pass both levels. The last test, which was done on the bike stem, is a fatigue test. The first one is alternating torque, and the second one is alternating bending. This experiment should be done only on one bike stem, and it should pass both levels, and you will see the result. So there is a workflow of a design process. First of all, you have idea, then you have some design space that you have to define the best one for your topology optimization software. The second one, there are some loadings, boundary conditions, etc. Then there is your results from the topology optimization. After that, you have to refine the model that can be printable and you can run the simulation on it. Then you have the step model, run the simulations, and then evaluate the results with a real experiment. So the topology optimization setting was ruled by weight. So I want to find some really nice shape with maximum weight of 100 grams. The final design that is shown on the picture has 98 grams. The computation time was about 8 hours. So if I select the smaller elements, it can increase the time, but it's not worth it for finding better solutions, because the bounding box that I used was really strict, and it was enough to keep this result. So there are results from the experiment. So the side bending, the simulation said that the worst scenario is more than 13 millimeters. Standard limit is 50 millimeters, and experiment shown 14.72 millimeters. So the experiment passed the standard. The second one is the bending forward. So the simulation set is 0.9 millimeter, experiment set is 0.05, and the limit is 10 millimeters. At this point, the regular bike stem has a really big problem to pass this standard in experiment forward bending. So this shape is very unique and it has a really good stiffness. So, and the fatigue experiment, there are some issues. So at the alternating torque, the bike stem failed and 3000 cycles. So I take the new one and run the alternating bending, and it passed with 100,000 cycles. So if you see what happened, so I run the simulations, or I run the finite element simulations again, and I found out some places where I was close to the yield strength of the material. So I had to do the redesign of this area and continue on work. So there is a conclusion. So the topologic optimized bike stem is lighter about 8.7%, but the main advantage of this design is that it has a really high stiffness during the forward bending. It's very important for downhill bikers, and also it should be necessary to reshape the problematic regions for passing the alternative torque test. So there are references from the pictures, and thank you for your attention.
Thank you, Filip.
So if you have any question, please